and run into through unsubstituted and substituted cyclohexanes, and maybe do acid-base stuff at the end. So what we want to talk about now, right, is we're working on the technology here. We're going to get it figured out, don't you worry. Right, so we talk about cyclohexane, and cyclohexane has a chair conformation, right? Cyclohexane is not flat like we draw it. Cyclohexane looks like this in reality, right? This is a chair conformation, and you probably remember this joke, right? Right here's the dude on the chair reading a book, hanging out at the beach, right? So that's your chair conformation, right? So in a chair, there are two types of groups on the ring. So we have, I'm going to overlap a little bit here. We have axial groups. So the red groups here are going to be axial. And axial groups point up and down. I'm writing with my finger, so if the text is a little bit messier than normal, I'm sorry. And then we have equatorial groups, and these are going to be blue. Right, so it's like super important that I spell stuff right, because this is going to be immortalized forever on the internet. It's like a tweet. You think you can erase it, but someone will save it. Right, so I can't mess up. So equatorial groups point out. / away from the ring. Right? So what I want you to notice is if you look at our axial group, if our axial group points up, right, so our axial group right here is pointing straight up, our equatorial group on that same carbon is going to be out and down. If our equatorial group on our next group here is pointing straight down, our hydrogen that is equatorial is going to be up in a way. So they're always slanted one way or the other, a little bit away from the ring, right? So your axial group is straight up, equatorial group is away and down, right? So we have our cyclohexane, our chair conformation, right? That chair, there's actually two chairs for every cyclohexane, right? And they go back and forth, and they do what's called a ring flip, right? So this is a ring flip. Now I'm not flipping I'm not just grabbing it and I'm not rotating it, I'm not doing this, right? I'm not rotating it around. Instead, what I'm doing is, let me erase that. So we're not doing this, no, not that. What's actually happening is we take this carbon here and we grab it and we pull it up, and we leave these four carbons, 1, 2, 3, 4, kind of where they are, and we pull this group right up here, and then we take the other carbon at the other end, we grab that, we pull it down, again leaving these carbons 1, 2, 3, 4 in place, and we do a ring flip. So we basically grab either end, either point, the red dot and the blue dot, and we pull the red dot up and the blue dot down, and we let the bonds between carbon 1 and 2 and 3 and 4, they rotate and get us from one chair conformation to the other. And this is a ring flip. Now, what happens, I'm going to redraw this, get a little cleaner for you, right? What happens in the ring flip is all the groups that were axial become equatorial, and all the groups that were equatorial become axial. So if I keep with my same color scheme here, we're going to start out with all of my axial groups being these red hydrogens. All right, and all my equatorial groups being blue. Right? When we do the ring flip that we just did above, what ends up happening is all of our axial groups become equatorial. Right? So they go from pointing straight up to they're pointing that out away from the ring. And then the equatorial groups, oops, sorry. Okay, we just erased part of our P. Like that happened. Take that, letters. Our equatorial groups end up becoming axial. So in a ring flip, axial becomes equatorial, and vice versa. Might have to go back to the pen because my finger can handle this for an hour, right? So we have our ring flip, we go from one to the other. The other conformation we need to talk about, right? The other conformation we're going to talk about is the boat conformation. So there are two main conformations you need to know for cyclohexanes. There's the chair and there's the boat, right? So this is the chair conformation. Oh, let's go back to black here. First erase this. Right, so we've got, that feels better. Right, we've got the chair conformation, and the chair conformation can become the boat. So basically what we did to get from chair to boat is that we took this same carbon here, we grabbed it, and we pulled it up. That got us there. And then we can get to our other chair. We can finish the ring flip if we go from here and pull this down. Right? So, yeah. So, right, so this carbon's here, and then to get to the other chair, right, we have just gone, right, so then this carbon here, right, is this one here. So, right, what you end up doing is just like we drew before, right? When we did the ring flip without showing the boat, we just grabbed red dot and blue dot, pull red dot up, blue dot down. When you show the chair, red dot goes up, blue dot stays up. You make the boat conformation. And then once you're in the boat, you pull the blue dot down and you get to the other chair. Now, when you look at these, the chair conformation, the chair is the most stable conformation. So these two here, these are the most stable conformation for our cyclohexane to be in. Right? The reason for that is like our bond angles are pretty close to 109.5. Right, we've already talked about they're around like 111 degrees. So really close to 109.5. And all of our hydrogens, if you were to draw a Newman projection, all of our hydrogens would be staggered. Right, so there are no eclipsing interactions at all. So if we look at a Newman projection, if we were looking at, again, my crappy eyeball drawing, right? We have a little crappy eyeball. We looked right here at this hydrogen, at this carbon, and then back to the other one. If you drew a Newman projection, you would see that all of those groups are in a staggered conformation. There's no eclipsing interactions, right? Now the boat is the least stable conformation. Let's put the actual word least in there. There we go. Is the least stable conformation. Again, if you guys thought my handwriting was bad with a marker, finger and pen on touchscreen is a nightmare. So the boat is the least stable conformation. The reason for this is mainly this flagpole interaction. Again, we went super hard nautical on this. So we have this flagpole interaction where the groups on either end that is up, they're close enough that they can bang into each other and interact, right? So this is a destabilizing interaction, right? The flagpole interaction, so the flagpole interaction is a transannular interaction, and transannular is just a big sciencey word for across a ring, right? So this flagpole interaction that destabilizes the boat occurs from across the ring. So one group on one side of the ring bangs into the other. Now, when you have no groups, when you just have cyclohexane, right, and you do a ring flip, there's no preference, right? These two conformations they are equally stable. Right? One is not higher or lower in energy than the other. Right? The reason for this is we have 6 axial groups in our chair, in our starting chair, and 6 equatorial groups. Right, when we do our ring flip, right, all our axial groups become equatorial, our equatorial groups become axial, and we go from 6 axial groups and 6 equatorial groups to 6 axial groups and 6 equatorial groups. So there's really no difference in these two structures, right? So they are the same energy. As soon as you put a substituent, as soon as you add a group to your cyclohexane, that changes the stability of your 2 chair conformations, right? So when you have a monosubstituted cyclohexane, your 2 chairs become different, right? So let's show you that. Apparently, I also draw with the mouse. Man, there's so much technology. The world is great, man. Okay, so let's say we have methyl cyclohexane. Right, start out simple. Methyl cyclohexane. So we draw our chair conformation. And we don't have to draw the hydrogens in. They're understood. Some are axial and some are equatorial, so you don't have to actually draw them in. Right? But we do have to draw in our methyl group. Right? So we can start out by drawing our methyl group here. Our methyl group, if we draw it like that, this methyl group is equatorial. Right? So this methyl group is pointing right down and away. That means that if you want to have the hydrogen for reference, the hydrogen there is axial, right? It's pointing straight up, right? Now, if I do a ring flip of this molecule, right? If I do the same ring flip that we've done, right? Again, we're gonna grab this carbon, pull it up. We're going to grab this carbon here and pull it down, right? We're going to ring flip it, right? Again, we're going to keep track of them here. Red dot carbon came up, blue dot carbon came down, right? And now our carbon here, our methyl group was equatorial, right? Remember when we do a ring flip, everything that was axial becomes equatorial, and everything that was equatorial becomes axial. So now, this methyl group points down. Right, so we go from, let's make this smaller. Boom, you get to see how the sausage is made. All right, so now, instead of that methyl group being axial, right, or sorry, being equatorial like it is here, it becomes axial, right? And there's a preference that in a monosubstituted cyclohexane, the more stable conformation has the substituent equatorial. Right? So if we're comparing these two cyclohexane conformations, this one is more stable. Oops. That's awful. Try that again. That was not a W, I promise. Right? It's going to be more stable, lower in energy, and this one's going to be might have to keep these in the right order. Right? This one's going to be less stable. And it's going to be higher in energy. Now, both of these conformations are possible, right? So again, if we had a bottle full of methyl cyclohexane and we were to take a snapshot, we would see most of our molecules would have the methyl group in the equatorial position, so most of them would be in this conformation here, right? And then the other and then the remainder would have the methyl group axial, right? So we always want to have our preferred conformation, our low energy conformation has our group equatorial. Now I guess the reason is why is equatorial preferred? Hopefully I spelled preferred right. That's the word I always like mess up. And if I did, I don't know, guilt. Right? Not like I have a PhD or something. Right? So why is being equatorial preferred? So there's two reasons. One is we can think about gauche interactions. Right, so you remember gauche interactions when we have a Newman projection. Let's just a little refresher here. Right, so we have a Newman projection. Gauche interactions happen when you have two non-hydrogen groups side by side in a staggered conformation. So right here, this is a gauche interaction. And I tried to erase that with my finger because I'm dumb. Say force of habit, not force of habit, right? Right, and the gauche interaction occurs because, right, the groups and the electrons on this group and the electrons on this group, they get close enough together that they bang into each other, right? And that's a destabilizing force. So how this relates to a cyclohexane, right, is let's have our methyl cyclohexane, and we'll have, I'm going to go to the next slide real quick. So we're going to have our methyl cyclohexane, you don't have to redraw it, right? We have our group axial. So if we draw a Newman projection, let's draw a Newman projection looking here, crazy eyeball, we're going to look right there. Right, if we draw a Newman projection for this, right, so our front carbon, the one that we're looking at, right, straight down, we have a hydrogen, and here you have to actually really care how you draw stuff. So hydrogen comes down, other hydrogen that is equatorial comes like that. In the back, we have this hydrogen here that is down and over, and we have this methyl group that is straight up. Now the other two groups are the ring. So 1, 2, right? So here's 1, 2, 3, 4. Sorry guys, I seem to have missed the carbon. I've done this tons of times, and I don't think I've ever missed a carbon before. 1, 2, 3, 4, 5. And the carbon you can't see is 6. So here's 1, 2, 3, 4, 5, and that makes 6 right there. If you're watching this semester, I've been on like hurricane for like 10 days. I'm allowed to be a little off because like I've just been sitting around like watching BoJack Horseman and stuff like that. So cut me some slack, right? So when we have our group axial, right? I have this gauche interaction because I have two non-hydrogen groups, carbon 2 and carbon 5, side by side. So here's one gauche interaction. And you're always going to have that gauche interaction when you have a ring. And then I have a gauche interaction here between my methyl group and my carbon 2 of my ring. Sorry, carbon 2 of my ring. Right? Now, if I have the other chair conformation, right? This one's a little harder, right? Here's carbon 1, 2, 3, 4, 5, 6, right? No, oh my gosh. Again, I'm gonna blame the hurricane. I am sorry. Existence is pain, in the words of Mr. Meeseeks. And if you don't get that reference, when you're not watching these videos, watch them Rick and Morty. 1, 2, 3, 4, 5, 6. Hey, there we go. Life is hard. All right, I'm sorry, guys. We're gonna get a tippy top here. We're gonna get there. Don't worry. We're gonna get there. Right. So we're gonna do the same. We're gonna look from 1 to 6. Right, this one's gonna be a little harder to see, but you'll come along with me on this magical journey. Right, so if we look here, we have a group up and over. Right, so we're gonna go up and over, and then carbon 6, we have hydrogen. Hydrogen's gonna be axial, so these are on opposite sides. And then the same thing. There we go. Right, so up front is 1, 2, 3, 4, 5, and then the hydrogen in the back you can't see is 6. So again, in this conformation, again, I still have, that was supposed to be red. Again, technology is wrecking me, guys. I still have that Gaussian interaction, right, that I'm always going to have with my ring, because it has to be two groups side by side to make a ring. So I have that Gaussian interaction. But when I make my group equatorial, what happens is that now this group is between two hydrogens, and there's no Gaussian interaction. So there's no Gaussian interaction with that methyl group anymore, right? Because there's a hydrogen here and a hydrogen here. So going from axial to equatorial, axial you have this extra Gaussian interaction between your substituent in your ring, and when you go to the equatorial position, you eliminate that Gaussian interaction. So that's one thing working in favor of having your group be equatorial, is you eliminate that Gaussian interaction. Right? The other thing is something called 1,3 interaction. Right? So 1,3 interactions are numbered a little weird, so you have to bear with me, and hopefully I won't punt my numbering like I just did a second ago. Right? So I'm gonna make this group axial. There we go. So 1,3 interactions is if we number from this carbon, we call this carbon 1. We go 1, 2, 3. The group that is axial at carbon 1 is close enough that it interacts with the group that's on carbon 3. So we get what's called you're killing me, pen. We get what's called right here, this is an A1,3 interaction, and the 1,3 is kind of the subscript on the A, right? The A stands for axial. So this is an axial 1,3 interaction. So it's the axial group at carbon 1 interacting with the axial group on carbon 3. And same thing, the other 3, so if I number again 1, 2, 3, again there's an A1,3 interaction here as well. Now we're numbering not like we're naming it, right? So what we're numbering is saying, hey, here's this carbon here, let's go 3 carbons away. So count it, 1, 2, 3. So on the third carbon from where the substituent is, I have an interaction there, and then I go the other direction, 1, 2, 3, and I have my group on my third carbon there. Right? So you have this A1,3 interaction when your group is axial. Now when you ring flip, now my group that was axial, right, this axial group here, becomes equatorial. Right? And it's pointing away from the ring. So now there's no group for it to interact with. Right? I have these hydrogens here that can have A1,3 interactions, but A1,3 interactions with hydrogens are very small. They're effectively 0. We don't count them. So when you make your group equatorial, you eliminate your A1,3 interactions. So our two things that we worry about is we worry about those Gaussian interactions in our Newman projections when we're axial, and we worry about A13 interactions. The thing that I will have you usually label, if I say like, hey, what destabilizes this chair conformation, right? I have you label the A13 interaction, so I want you to show those interactions, right? So, for example, right, I don't know why I'm at the right of D. Again, I blame her rotation. Right? So let's say I was like, draw isopropyl. See, when I make a mistake and there's a whiteboard, there's not this like big dramatic like smashing of the screen. So draw isopropyl cyclohexane. Right? So you can be like, oh, I can draw isopropyl. So let's see, draw isopropyl cyclohexane. Right? Draw a chair conformation. Right? Ring flip that chair conformation. Label, wow. Label the most stable conformation. Right? Draw the destabilizing draw the destabilizing interactions on the least stable conformer. All right, so these are trying to be how a test question would look, right? So we've got to draw isopropyl cyclohexane. I will wait because you can hit pause. Hit pause. You didn't hit pause, did you? Hit pause. The joke never gets old. All right, so you're going to draw isopropyl cyclohexane. You're going to draw a chair. I don't care what chair you start with. I'm going to draw the equatorial one because I can. But if you want to draw the axial one first, that's perfectly fine because you're going to ring flip it. It's the next part, and you're going to get the axial conformation. So it doesn't matter if you start axial, you're going to ring flip to equatorial. You start equatorial, you're going to ring flip to axial, right? So again, just keep everyone on the same page. Red dot comes up, goes here. Blue dot comes down, goes here. Right? So now which one of these two is most stable? Okay, the most stable one is going to be the one that has your group equatorial. So this is most stable. Right? And then this is our least stable conformation by process of elimination. Right? So now draw the destabilizing interactions. And so the interactions that I'm going to look for here, and then I want you to show both A13 interactions, right? So we're going to draw on our hydrogen here and here. And I'm going to have, I always try to draw it like this, right? These two groups bang into each other. That is one of our A13 interactions. And then these two groups bang into each other. And that is the other A13 interaction. So you're going to want to label both A13 interactions when we do something like this. Hogely Undogly seems okay? Awesome. So that's what you need to be able to do, right? You need to be able to take the name, draw the structure, draw the chair conformation, ring flip the chair conformation, figure out which one is most stable, and then label the A13 interactions. Now, so what I'm going to point out is, I said that when we have, that should have been black. Okay, screen, stop mocking me. All right, so, right now, I'm going to use R here. So as we change what the substituent is on our ring, we change the ratio of our conformations, right? So bigger R group, so the bigger the R group, the more equatorial we're going to have. So if we have 100 molecules, right, and R is methyl, right, we might have 90 of the conformation where R is equatorial and 10 of the conformation where R is axial. These are numbers are just like ballpark guesses here, right? When we have ethyl, right, so we've gone, so Me, let's make sure everyone's on board here, Me equals methyl, right? Et equals ethyl, right? I always forget to do this every semester, so I'm going to make sure I do it now. So I'm going to do IPR equals isopropyl, and then T-butyl is tert-butyl. Sorry that my handwriting's bad. Right, so if we go ethyl, ethyl is a little bit bigger than methyl, right? There's one more carbon, but it's not that much bigger. It's like 95 to 5, right? And then we have isopropyl. Isopropyl has 2 extra carbons, we're like 98 to 2, right? So as the groups get bigger, there's a greater preference for them to be equatorial. And that's because as that group gets bigger, the A13 interaction that you see gets bigger as well, right? So when we go to tert-butyl, right, that is 100 to 0. Tert-butyl can never be axial. Never axial, right? If you draw tert-butyl axial, he will come to you when you sleep and he will kill you. Tert-butyl cannot be axial, right? Tert-butyl is just too big. Having those 3, right? So going from methyl to ethyl to isopropyl to tert-butyl. Tert-butyl is just way too big to be axial. So you always, always, always have it be equatorial. So as your groups get bigger, there's a greater and greater preference for them to be equatorial. Right? So those are all the takeaways I wanted you to get for cyclohexanes. Right? Equatorial is always more stable when it's monosubstituted. The axial configuration is possible, except for when the group gets really large, like tert-butyl. And the reason that the axial group the axial position is less stable is because of A13 interactions. All right, so we're going to finish up these physical properties by doing a little bit, I don't do a lot, a little bit of acid-base discussion, right? So we're going to kind of define our 2 types of acids and bases, right? The first type are Bronsted acids, right? So we're going to talk about acids and bases. Oh my gosh. Right. So we have Bronsted acids. And Bronsted acids are your traditional Gen Chem acids and bases, right? Acids donate protons, so give H plus, and bases accept protons, right? Take H plus, right? Now, you learned about pH in Gen Chem, but pH is a scale that's measured in water, right? For things to be, pH is how many protons are there in water. Well, organic molecules are greasy and don't dissolve in water, so the acid scale that we use, right, is the pKa scale. Right, so the pKa scale is a scale we use to measure acids and bases in organic chemistry, because it doesn't rely on water. Right. So what we're going to do here is, so when you have a large pKa equals not very acidic, and then a low pKa equals very acidic. So the lower your pKa, the more acidic you are, right? The scale roughly runs from 50 to about -20 is the scale, right? So I'm not going to have you, I don't care about you knowing the numbers, I care about you knowing the trend, right? So I'm going to give you the numbers just as a point of reference, but it's not like you need to know them. So simple hydrocarbons, simple alkanes, like the hydrogens on methane, that pKa value is around 50, right? Now, as you go, when you go from an alkane to a double bond to an alkene, this hydrogen has a pKa of about 40. Now, between alkene and the next carbon, we have amines. I'm going to say about 40. And amine, so either a secondary amine or a primary amine, pKa is around 35, give or take. Then we have alkynes. So terminal alkynes were the hydrogens at the end of the alkyne. This hydrogen here, so I'm highlighting the hydrogen, right? This, drawing the hydrogen, this one, and one of these guys. Right, these are the hydrogens I'm talking about. The pKa of that is around 30, right? Then we have things like ketones. So this hydrogen's around 20-ish, 20 to 25, somewhere in there, depending on what the structure is. And I'm really good with the board here. I'm going to run out of space. And then we have like alcohols, those, and water. Alcohols and like H2O are 15 to 18, give or take. All right. So sorry. So this is less acidic. And this down here is more acidic. So acidity is increasing as we go across, right? Now, I don't really care about the numbers. I want you to kind of know the general scale, right? That we have alkanes, then alkenes, then amines, then alkynes, then ketones, esters, aldehydes, things like that, and then alcohols and water. So the reason this matters is knowing pKa's allows you to predict reactivity. So if you have a reaction where you have an acid and then a base, you can make, right, the conjugate acid and the conjugate base. We just got all Gen Chem up in here, right? The general rule of thumb, or not general rule of thumb, the rule is that acid-base reactions, that noise is going to live forever now. I drew a little person on accident. Sorry about that. He looks as confused as I am right now. And then we have our conjugate base. And the way these reactions work is that, right, you always go to make reactions make the least acidic compound possible. So those are actual letters, I swear. So if you have this plus, right, you can ask the question and answer the question based on pKa's. Does this reaction occur? Does this reaction happen? Does the reaction favor starting materials, SM, or does it favor products? And you can determine that by looking at the acids. So you can compare this acid to this acid. The reaction will go in the direction of the least acidic compound. Right, so I go back a slide, hey, right? Simple alkanes have a pK of 50, that's less acidic than an alcohol, right? So with alcohol on the starting material side, we have an alkane on the product side. So the reaction is going to go towards product, so reaction happens. Right, the reaction happens because this is more acidic and this is less acidic. I think we're going to get cut off a little bit, that's all right. So you can look at a reaction. We'll do one more real quick. Okay, I like punt under the pressure, man. So we could look at would this reaction occur? You can check, you compare this acid to this acid. This is pKa 35, this is pKa 18. So the amine is less acidic than the alcohol, so the reaction would not happen. So the reaction favors the starting material. And I think we're going to cut it close. So I think I'll stop here and I will do Lewis acids at another time. So that's one down, a few more to go. All right, thank you. To predict reactivity. So this is what I kind of ran through at the end, right? So you want to have, right, if I have my acid, if I have some base, and then the reaction happens. Oops. The reaction, and then I have a reaction drawn up that needs to be smaller. So big. The reaction happens, or the reaction is written, I shouldn't say happens, right? If you want to know if that reaction actually can occur as written, right? You compare the two acids, and reactions always try to make the least acidic thing. So you look at this acid here and compare it to this acid here. The further to the right the acid is, the less acidic it is. So you want the least acidic acid on the starting material side, so this is our starting material side, and the more acidic and the less acidic acid on the product side. So you want more acidic starting materials, less acidic products. So if we look, alkynes are further to the right than amines. So the alkyne is more acidic than the amine. If we look, our more acidic acid is on the starting material side, and our less acidic acid is on the product side. So this reaction would occur. Reaction occurs as written. As shown, right, we go from starting material to products because we go from a more acidic compound, our alkene, this hydrogen here, to a less acidic compound, our amine. Right? So this is a kind of acidity that you are used to, right? You're looking at the movement of protons. There's another type of acidity that is a little bit less normal, I guess is the term, less intuitive, and that is Lewis acids and bases. And Lewis acids and bases, the Lewis theory doesn't look at the movement of protons, it looks at the movement of electrons, because we can have things that can act as acids and aren't necessarily protons, right? So we look at Lewis acids and bases, right? So Lewis acids and bases. Lewis acids, these will accept electrons. Right? They have an empty orbital. That will that can take electrons. So you have to have an empty orbital, and then that orbital can be filled by electrons. And those electrons come from Lewis bases. These donate electrons, right? Lewis bases almost always have a lone pair of electrons. So we're donating some lone pair to these, to our Lewis acid. Lewis acids are often metals or metalloids. So that's often what we think about for Lewis acids as metals or metalloids, right? So if we kind of think about it, or as an example, right? So if we have a carbonyl compound, okay, that I was gonna try to let it slide, but that I was way too messed up. I felt bad, right? So you have this oxygen here, and this oxygen has two lone pairs, right? Since it has lone pairs, right? So we got our lone pairs here, right? This oxygen is a, let me get a different color here. This oxygen is going to be a Lewis base. Right? It has lone pairs that it can donate to something. Right? And one of our my kind of quintessential go-to Lewis acid is BF3, right? So this is going to be a Lewis acid. So here's where I want you to have a little bit of Gen Chem in your life, right? So if you remember, boron is the oddball of the first kind of first row of the periodic table. Remember, boron doesn't ever have an octet. Boron always has 6 electrons around it to be neutral. So boron always has an empty orbital, right? And that orbital can be filled by electrons. So what happens is these electrons here go into that orbital. I don't know why it does that to me. Stop it. Thank you. Go into that orbital and we make this complex where the oxygen is bonded to the BF3. Now, remember when we talked about 4 mole charges, right? Our oxygen gave away 2 electrons, right? It just went from having those 2 electrons to itself to sharing them. So that means that it gets a positive charge, right? You can also think about it as, right, oxygen with 2 bonds is neutral, right? We have 1, 2 bonds. Oxygen with 3 bonds, 1, 2, well, that's 2, 3. Oxygen with 3 bonds has a positive charge, right? Since we can't destroy or create electrons, if we get a positive charge, that means our boron gets a negative charge, right? Which makes sense. Our boron got electrons, so it gets a negative charge, right? So this is how Lewis acids and bases work. You're not just confined to protons, but the Lewis acid base theory also explains Bronsted acids and bases, which is important, right? They need to be consistent, right? So if we look at a proton is a Bronsted acid and it's a Lewis acid, right? Because think about it, it can accept electrons. So if we have our carbonyl again, right, I'm going to click back over. Our carbonyl, right, a carbonyl can be a Bronsted base because it can accept a proton, and a Lewis base because it can give its electrons to something. So a carbonyl is a Lewis base and a Bronsted base. Right? And a proton is a Lewis acid and a Bronsted acid. Right? And so again, what can happen is, right, if you're thinking about it on a Lewis base, Lewis acid concept, right? These electrons go out and are given to the Lewis acid, and we make this, right? Again, oxygen has 3 bonds, so it's positive. Right here, I start out with an H+, so I don't have to have my Hb-, right? My charges stay the same, right? Over up here, right? Neutral thing plus neutral thing. I have to have something that is overall neutral, right? So plus minus is overall neutral. Down here, neutral and a positive thing, I have to make something that's positive. So we think about a Lewis acid base. Here's my Lewis base, and it is reacting with my Lewis acid. Similarly, we can think about my H+ is a Bronsted acid, and it's reacting with this base, these lone pairs as a base, to get the same thing. So Lewis acids and bases explain how Bronsted acids work, where H+ is just a Lewis acid, as well as covers things that aren't H+. So it gives us a way to explain why boron reacts with the lone pairs on an oxygen. All right, so far, so good.